Hello folks, thank you for joining Platform Line Systems webinar on 7 steps recipe for continuous integration using OpenStack. My name is Madhura Miskaski and I'm joined here by Big Lee today. And let's take a couple of minutes to give folks enough time to join in before we get started. Okay, let's get started folks. Hello and welcome. Good morning, good afternoon, or good evening to you folks who are joining us from different time zones. My name is Madhura Miskaski and I'm the co-founder and VP of product at Platform 9. And I'm joined here today by Big Lee, who's the co-founder and chief architect at Platform 9. And we are here today for Platform 9 Systems session webinar on 7-step recipe for continuous integration using OpenStack. So let's get started. Here's a quick agenda for today's session. We're going to start by looking at the benefits of a 100% automated CI/CD workflow for organization or a DevOps team of any size. We're then going to look into what role can OpenStack play towards letting you achieve this goal of 100% automated continuous integration workflow. And then we're going to dive into the process. So we're going to talk about requirements to get your CI/CD automation in place. I'm going to share a sample recipe including hardware specifications for one of our internal environments. And then I'm going to hand over to Book, who is going to talk about the detailed 7-step procedure for automating your CI/CD workflow. And he's going to share plenty of examples using our code base. And we're going to leave enough time at the end for question and answers. But I encourage you folks to make this an interactive session. So feel free to ask questions as and when they come, and we'll try our best to address them. So quick introductions. My name is Madhura Miskaski. I'm co-founder and VP of product at Platform 9 Systems. Before starting Platform 9, I was a staff engineer at VMware, where I spent 7 years or so, primarily as a technical lead or architect in different parts of VMware's management portfolio, including VMware vCloud Director, VMware vCenter, etc. Before that, I spent a couple of years in R&D team at Oracle, and prior to that, I was pursuing masters at Stanford. And I'm joined here by Big Lee, who is our co-founder and chief architect at Platform 9. And before starting Platform 9, Big was one of the earliest engineers at VMware. He was engineer number 14 at VMware, and he grew to be a principal engineer there. And he was the primary innovator or architect behind a number of key products in VMware's portfolio, including P2V converter, virtual device management, virtual application management. These are just few examples of various products that Big helped design and architect. So let's get started by first talking about the importance of a completely automated continuous integration workflow. And I'm going to speak a little bit from the perspective of Platform 9. We are a SaaS company. What we do is we make production-grade OpenStack available to our end users as a service. And so from that perspective, one really important metric that our development team gets measured by is how quickly can they ship code, how often can they ship code, while maintaining a very high confidence in the quality of the end product or the code that gets shipped. And this is really an important metric for any DevOps or development organization beyond a certain size. And so if you look at what is required to achieve this goal, one of the key ingredients that a build or infrastructure team of an organization must really supply to a development team to help them achieve this goal is really a 100% automated continuous integration infrastructure or build infrastructure, which has a number of benefits. A fully automated continuous integration system encourages developers to ship high quality code and do that often enough, because once the developer has built in his change set or his code changes, he then pairs it with the appropriate amount of tests, unit tests, integration tests, and so forth, and then he hands it over to your build or infrastructure system, which then takes up that change and really thoroughly tests it by simulating different scenarios, standing up the right infrastructure to be able to test that code. And if there is a problem in the code base, then the developer is automatically notified. If there is no problem, then the code automatically gets checked into your main branch of your source code. And all this happens while the developer is free to switch to something else, spend his time fixing some other bugs or working on some other code. So this significantly improves development efficiency. And it also encourages a culture of test-driven development, where because you make it so much easier to run test cases, developers are encouraged to write more tests. So now that we've looked into the benefits of an automated continuous integration workflow, let's talk about what advantages does OpenStack offer towards achieving this goal. So for those of you who may not be familiar with OpenStack, OpenStack is an open source, open foundation project. It's one of the most thriving, one of the top most popular open source projects today. It has a very active and thriving community, along with a strong sponsorship and support by a number of key organizations in the enterprise infrastructure space, such as Cisco, VMware, Rackspace, EMC, IBM, so on and so forth. And OpenStack has really started setting a standard by which private clouds of today and future are being built. Right? And OpenStack offers a number of benefits for running your private clouds as efficiently as public clouds are run. And OpenStack supports a number of use cases where running a continuous integration workflow can be just one of the several use cases that OpenStack can help you run. And one of the big benefits of OpenStack from the perspective of continuous integration workflow is the efficient utilization of resources that it offers. OpenStack comes built in with an automated placement engine, which looks at the requirements of virtual machines and properties of underlying resources, and it places virtual machines on appropriate resources while keeping your policies that you as an administrator has set up in mind, and also giving you the choice of setting the appropriate levels of oversubscription or over allocation of resources. So this really gives you the tools to get the best utilization out of your infrastructure in an automated way. And then on top of this, OpenStack has a number of built-in constructs that really help towards building that automated CI/CD workflow, such as having a standardized catalog, a glance catalog of virtual machine images, having the right customization constructs. For example, each developer can upload his own SSH keys, which can then be injected into virtual machine images as and when they're getting deployed. Virtual machines can be tagged with simple key value pair tags, very similar to what Amazon EC2 offers. And tagging can be a very powerful way to then annotate your virtual machines with appropriate information and consume it at runtime. OpenStack has built-in support for CloudInit-based customization, which is an open source standard for customizing virtual machine images. And CloudInit is a powerful tool that lets you do a number of things, such as injecting Chef for Puppet or Ansible scripts into your virtual machines once they are powered on and acquire an IP address, which again facilitates better end-to-end customization, which is a key in running a continuous integration workflow. And then you can snapshot your virtual machine images at any point in time to create new golden VM images out of those VMs. And all this is available via simple, intuitive, RESTful APIs, as well as CLIs that OpenStack offers. And finally, from a DevOps perspective or an IT administrator's perspective, OpenStack gives you the right constructs to give you enough visibility into your infrastructure as it's running. So what we typically recommend is that you run your CI/CD infrastructure in a dedicated tenant in OpenStack, so that you can allocate appropriate resources to that tenant and avoid any noisy neighbor problem, and also monitor that tenant appropriately. But then OpenStack gives you the ability through its dashboards and its reports, etc., to look at all the active workloads that are running. If a number of them are running into an error, an administrator can quickly pause them and snapshot them at that point in time and then share them with appropriate developers so that those developers can immediately start debugging those scenarios. So these are just added benefits from an IT administrator's perspective. Okay, so now that the benefits of OpenStack are clear, let's start by talking about the recipe for continuous integration. We're going to start by talking about the requirements. The key requirement, of course, is an OpenStack private cloud that has been funded with sufficient amount of resources, right? And there are several options here for you. You could go with an open source OpenStack and download it and deploy it. Or if you could partner with an OpenStack vendor such as Platform 9, where we make it extremely easy for you to go from just a bunch of infrastructure to a fully operational OpenStack environment. Or you could go with a hosted OpenStack model, where the OpenStack provider is not only giving you the OpenStack software, but also the hardware that is backing it. Regardless, it's your responsibility to make sure that the OpenStack cloud is funded with sufficient amount of CPU, memory, storage, and network resources. Here is a quick spec of one of our internal systems for reference. So in this environment, we have about 100 gigahertz of compute, 500 GB memory, and about 2.5 terabytes of storage. And this is spread across about 5 or so physical servers. They are AMD Opteron G5 model servers. Couple of them are 2-socket with 3 gigahertz and 12 cores each, and a couple of them have a slightly different configuration. Each server is equipped with 100 gigabytes of DDR3 SDRAM memory and about 500 gigabytes of storage, and they costed us about $4K per server. In terms of over allocation ratios, we heavily over allocate on compute because that rarely tends to be a bottleneck in our environments, and this typically tends to be true in most environments. So on an average, compute tends to be 5x or 6x over committed, but we have set it up so that it can overcommit up to 16x. With memory, we tend to be a little bit more conservative. So memory over allocation is allowed to be up to 1.5x. But in practice, we tend to not reach those levels, especially because we tend to run non-test workloads side by side with test workloads at times. And so if you have heavy memory over commitment, then it can slow down some of your non-test workloads. And this is also why we recommend running your CI/CD in a dedicated tenant if you can. And then storage in our setup is all heavily shared. It's all QCOW2 based, so it's all copy and write storage. It also tends to be a bottleneck, so it is a factor we tend to watch or monitor fairly closely. And then in terms of workload, we run about 1,000 virtual machine instances. About 1,000 VMs get created or destroyed each day on this setup. On an average, about a few hundred VMs are running at any given point. Typical VM config is 1 vCPU, 1 GB memory, 10 GB storage, or 1 vCPU, 4 gig memory, and 8 gig storage. And these are just flavors that we've captured in our Platform 9 managed OpenStack environment so that it makes it really quick for them to be consumed. You need your glance image catalog filled with a bunch of vanilla VM images for operating system versions that you're going to use in your CI/CD workflow. And what we recommend is you start with just your minimal OS VM images that are equipped or enabled with Cloud Init. These VM images are something Platform 9 ships out of the box with its own managed OpenStack deployment, but you have various ways to get access to these VM images. And what we recommend is you customize them dynamically as part of your CI/CD workflow. Finally, a right tool for automating your CI/CD pipeline. The two most popularly used tools today are Jenkins and TeamCity, and they have their own pros and cons. Jenkins is open source, it's free. It's been one of the most popular CI/CD tools for several years now. And we've had extensive experience using it both at VMware and in early days at Platform 9. The difficulty with Jenkins is that it tends to have a number of plugins for every functionality that you want to run with it. And many times the burden is on you to select and test the right plugin. Versus TeamCity is a paid proprietary product. But the large benefit that we found with it is that a number of useful functionality is just provided out of the box. So you don't end up wasting your time finding the right plugin for it. You need a good version control system. Every development organization will have their favorite one. We use Git and we love it. It has a number of benefits. It's extremely efficient. It has super fast branching. It makes full history of changes available to you even when you're offline. And it has a number of its own benefits. But the difficulty with Git is that it tends to be a complex system, especially initially. It has a pretty high learning curve. But if not Git, you will have your own favorite version control system, such as Subversion or something else. Okay, at this point, I'd like to hand over to Bickley, who's my co-founder and chief architect at Platform 9 Systems. And Bic will take over and walk us through the detailed 7-step recipe for automated continuous integration.
Okay, thank you, Madhura, for the handoff. So let's start part 2 of this presentation. And what I'm going to do is go into the details of this 7-step recipe that Madhura talked about. One second. All right. Okay, so let's move on to the recipe. So we use OpenStack to help us automate our continuous integration pipeline for building, integrating, and testing our own Platform 9 product. So the first thing I'm going to do is talk a little bit about the product itself that's being built so that you can understand a little better how it flows through the pipeline. We'll then talk about the architecture around these elements of continuous integration and testing, and go over how the various building blocks flow through the pipeline. Once we're done with that, I'm going to talk about specific OpenStack cloud features that we found especially useful in our automation. Okay, so now let's talk about what's being integrated, what's being built and tested. So in this presentation, although we're going to talk about OpenStack as a tool to help us achieve these goals, what's interesting is Platform 9 itself, the product, is an implementation of OpenStack. And I'm just going to briefly describe what Platform 9 is. So Platform 9 is an OpenStack private cloud that is offered as a service to our customers. So when we deploy a private cloud for a customer, we first deploy something called the OpenStack controller, and that's the big box that you see at the top of this picture. It contains a bunch of software components, and in order to deploy a cloud, in addition to the controller, what we ask the customer to do is to select a number of hardware nodes, which are shown at the bottom, and then install the Platform 9 agent on each of these machines. And the agent is downloaded from the controller. Once those agents are installed, the customer specifies for each node what role it's going to play in this cloud. For example, is it going to serve as a compute node or maybe a block storage node, etc. Once that selection is made, the Platform 9 OpenStack controller will then deploy the correct OpenStack agents onto each of those machines, and then establish communications between those agents and their manager components that run in the controller. Okay? So that was kind of a brief overview. What's important here to see is, if you look at where the software comes from, it originally comes from the controller, right? Everything is packaged inside of that controller. So, in other words, our product is built from smaller components. Those are the little rectangles that you saw in the big box. And for those components, we treat them as single-purpose, self-contained. We dedicate a Git repo for each one of those components. And each component is self-contained in that it specifies its own build script and unit tests And when we build a component, what that produces is an artifact, which is either an RPM or a tarball. Now, the overall product is really a grouping of all of those components. And since the collection of those RPMs and tarballs are eventually going to end up in something that will run as a cloud instance or a cloud virtual machine, the most logical way for us to package the product is this image, this cloud image, and we'll talk about how we build it. This is a controller image. Sometimes we refer to it as a deployment unit image, so you'll see this term DU image quite a lot. Okay? So that's the building blocks of our product. So let's talk about how we build the product from the components to the final image. And let's start with those components. So the way it works is, as I said, each component is mapped to a single Git repo. And when a developer is ready to commit a change and push it, we ask the developer to push the change not to the master branch of the repo, but instead to something called an auto-merge branch. Now, when a change is pushed into auto-merge branch, we've configured TeamCity to detect that event and then start step 2, which is to build the component. And this has many sub-steps that start with checkout and then build and run the unit tests for that component. We then collect the artifacts, such as the tarball or the RPM. And if the result of the build is success, then TeamCity will perform something called an auto-merge. That means it'll take the change from the auto-merge branch and then automatically push it onto the master branch. Okay? So this happens all the time and continuously as changes get checked in to auto-merge. All right. So now that we've seen how the individual components are built, how do we go from here to the overall product? And before we get there, here's a summary of the 2 steps that I mentioned, and I'll leave this here for reference. So going back to what I was saying, how do we go from components to the overall product? So the way the overall product is built is it depends on components, and some of those components themselves may depend on other components. And so there's this concept of a dependency tree. And if your CI engine or product or tool is any good, it should allow you to express these dependencies. And luckily for us, TeamCity does a very good job. And what I've shown here is a graph that shows you the flow from the dependent components into the final product build, which is shown in the upper right corner, which we call the DU AMI build. Okay? So let's see in detail how that works. So we've configured TeamCity to observe changes to these components. And in particular, when there's a successful build of a component, as I shown earlier, then TeamCity will trigger a build of the overall product, which will ultimately produce a cloud image. However, since there's a lot of churn, we don't want TeamCity to do that on every single detected change. So instead, we tell TeamCity to check every hour so that we don't waste too many system resources spinning too many builds. Okay, so when TeamCity detects those component build changes, what it does is it checks out the integration repo that represents the overall product. And it also checks out all the dependent artifacts from all of those dependent components. And it kind of gathers everything into one big bundle. It then runs the integration scripts that are stored in the integration repo, and it passes it all those artifacts that we spoke about earlier. Now, for the first time, this is where we take advantage of our internal OpenStack private cloud. Because remember that our product is going to be packaged as a cloud image, and in order to build a cloud image, you need a cloud. So our integration scripts interact with our OpenStack private cloud through various ways. OpenStack provides very solid REST APIs, so you can, from your scripts, you can invoke HTTP requests or use a convenient wrapper, such as a Python client library, and I'll show you some examples. And the other method is OpenStack also provides very solid command line tools, and I'll also show you an example of that. So let me switch to a code view here. Let me show you an example of how we use the CLI tool. So CLI tool is very convenient when you want to automate something with OpenStack, but do it in a quick and dirty way. For example, here we're doing it from a bash script. And so in this example, we're calling the Nova command line utility to check on the status of an image. And depending on the output of that tool, we'll then make some decisions. Now, when we want to do something more advanced, or do it from code that will be edited by multiple developers, we prefer to use Python. And in particular, we don't use the CLI tool anymore, but instead we use one of the wrapper client libraries that OpenStack offers. And those are available for multiple languages, and in this case it's Python. So for example, here we're using the Nova client to talk to the Nova API, which manages compute resources. And we're also using the Cinder client to communicate with the services that manage block storage. Okay. So let me show you an example of the Nova client. So here, for example, we're using the library to get the list of all instances or servers. Okay? So let's go back to the presentation. Okay, so the first step in creating the cloud image is to create a temporary instance. Okay, so an instance is a virtual machine. And we take advantage of OpenStack's image catalog to store some standard operating system images, such as CentOS or Ubuntu. In our case, we use CentOS as the base operating system for our product. So we create an instance from that image, which is at this point pretty bare, right? It's just it's just the operating system. What we do next is we use a tool called Ansible to install the artifact of our product into this instance. You can use other config management tools such as Chef or Puppet, or you can also script it yourself using Bash. It doesn't really matter. The way you automate it is up to you. But in our case, again, we're using Ansible to populate this instance with our software. We also do things like patch the OS to make sure it has all the security patches. And when we're all satisfied, we shut down the instance and we take advantage of OpenStack's snapshotting feature to create an image out of that instance. Okay? We hope that this image will eventually become useful, and in other words, something we call a golden image. Okay? But before we get to that point, before we know that this image is any good, we actually need to run some tests. And this is where we invoke the integration tests that will exercise the software that is stored in this DU image. Now, each integration test needs its own isolated environment that represents a full deployment of our product. Okay? And again, our product itself is an OpenStack private cloud deployment. So to create these isolated environments, for each test, we create something called a pod. A pod is simply a collection of virtual machines or instances. So in step 4, we create one pod per test, and we create it from the DU image and also from the OS images. And we configure it and make it ready for the tests. Once the pods are ready, that's when we invoke step 5, which is to run the integration tests themselves. So as I said earlier, a pod represents a full deployment of our product. So when we create a pod, we will deploy an environment that looks very much like what our customers would see. So it will have an OpenStack controller. We will automate or simulate the installation of the agent, and we will also automate the installation of the OpenStack agents, and then we establish communications. Once that's done, we run the integration tests, and our number of integration tests keeps increasing. These days, we have about 24 at least integration tests. And what they do is they exercise product features and things that the end users would see. For example, uploading images to their private cloud, spawning instances, or connecting instances over a virtual network. And since an instance of our product is an actual OpenStack deployment, we can take advantage of the same automation mechanisms that OpenStack provides, including REST APIs, CLIs, and we also use something called Fabric to automate running SSH commands inside of instances. Fabric is a Python library that is pretty popular for doing this. So in summary, to build the product image or the cloud image, we set up TeamCity to start the build and test cycle if one or more components have changed and have been built successfully. We then create and configure one pod per integration test, and then we run the integration tests. In step 6, what we do is we determine the overall status of the tests. So if all tests succeed, we consider the overall build to have passed, and we tag the image, that DU image that we produced, with a flag that says that it was successful. Okay? And in step 7, we clean up any resources that have been left behind by the build and integration test process. Now, we do that on a selective basis. For example, a build and test run will create many instances. But if the build failed, then we want to preserve those instances so that engineers can go and log into them and try to troubleshoot what went wrong. And the counterpart to that is if a build is successful, then we tend to delete instances immediately. Images, we keep them for a while so that we can reuse them. But regardless of what we do, in general, all objects are subject to eventual pruning. Okay. Pruning means they are eventually deleted after some grace period. This is something we learned very early on, and that is it's very important to have a resource pruning job for your CI environment. And the reason is when you're using a private cloud as the main automation tool for your CI pipeline, you're going to be creating objects, and a large number of objects all the time. Instances, images, and if you don't have a pruning job, your private cloud is going to fill up very quickly. Okay? So our pruning job is another TeamCity scheduled job that periodically goes and looks for objects that are older than a certain grace period. And if they exceed that period, it'll just go and delete them. There are some exceptions to the policy. So for example, we try to keep the last known good image so that we can reuse it. And sometimes there are objects that need to be kept for one reason or another. And also some of our developers create their own personal development environments on our private cloud. So for that, we use a special tag called don't delete. And if the pruning job sees that flag, it'll just skip over the object. Let's go over some OpenStack cloud features that we found extremely useful in our automation. As I said earlier, when we start a build and we run integration tests, we spawn many, many instances. And in OpenStack, when you spawn an instance, you give it a flavor, and the flavor specifies how much memory and disk and how many CPUs to give to that instance. And we want to be smart and only give what's absolutely required for every test. Okay? So we take advantage of these flavors by creating many, many flavors and then tuning them as necessary and adapt them to the actual workloads that need instances. So for example, let me go to my console here and show you the various flavors that we've created for our various workloads. And you'll see that there's a lot of them because, again, various workloads have different needs in terms of memory, disks, and CPUs. Okay? So by using these flavors, you can make more efficient use of your cloud. Another thing we found pretty useful is host aggregates. Okay. So what this means is when you tell OpenStack to spawn an instance for you, it'll look at the flavor parameters and then it'll determine one compute host that has enough resources to satisfy the request, and it'll do some form of load balancing depending on statistics on resource usage on various compute hosts. And for the most part, it does a pretty good job of doing that. But sometimes you want to tell OpenStack to place an instance on a particular set of hosts. And one example of this is in our environment, we often have workloads that require running one virtual machine inside of another, and we call that nested virtualization. Whenever we need nested virtualization, we take advantage of host aggregates. So a host aggregate is a grouping of one or more hosts that allow you to bind special flags or metadata to that group. So for example, in our environment, we have a set of hosts which satisfy this nested virtualization requirement. And it's called Ubuntu hosts, don't delete, okay? And what I'm showing here is this aggregate specified the UUIDs of the hosts that belong to the group, and it specifies one or more flags for that group. And in this case, it says nested virtualization equals true. Now, when we spawn an instance that requires this feature, we use a special flavor, and we add that same flag to the flavor. Okay, so here we have this flavor called 1 CPU, 1 GB, same disk, and you'll see that it has that same flag. So whenever we create an instance with this flavor, we're telling OpenStack to look for a host in a host aggregate that can satisfy that requirement. And finally, tagging. We've talked a lot about this. We use tagging everywhere. We tag our instances, we tag our images, and we use those tags for many, many different purposes. And tagging with OpenStack is incredibly easy, and it's very easy to look up objects based on those tags. To give you an example, let me show you the metadata tags that are associated with one of our images. And this image is the result of the build. And as I said earlier, we tag images with the build results. In this case, you can see that we tagged it with fail as the value and test result as the key for that tag. Okay, so I hope that was a pretty useful overview of how we take advantage of OpenStack Private Cloud in order to automate our CI processes and help us be efficient and maintain a very high quality level for our product.